Welcome back to the analysis seminar. Our speaker today is Mingming Cao from ICMAT, and his title is Absolute Continuity of Elliptic Measure in One-Sided NTA Domains Satisfying CDC.
Okay, thank you, Jose. Today I'm going to talk my recent work about the absolute continuity of elliptic measure. This is a general work with Oscar Dominguez, Chema Mateo, and Pedro de la City. Recently, our work has been done to seek necessary and sufficient conditions on the geometry of a domain to ensure that the elliptic measure is absolutely continuous with respect to the surface measure. Hoffman, Mateo, Mibarda, Tosa, and others have made many efforts in this direction. Through research involves the intersection of harmonic analysis, PD, and geometric measure theory. Their work can help us to understand some subjects better, such as the solvability of second-order divergent form elliptic operates on rough domains, and the ratifiability and the absolute continuity of elliptic measure. We will talk their work below. Our topic also belongs to this field. In particular, in this talk, we will study the following three aspects. One, the behaviors of the solution U of L. Here, L is the second-order divergent form elliptic operator. It contains the Carson measure estimate, non-tangent maximum function estimate, and the square function estimate. Two, the geometry of a rough domain omega. In this talk, we will use the Kirk-Rule condition and Hannock chain condition. Three, the regularity of the boundary. It involves ratifiability, uniform ratifiability, and the absolutely continuous of elliptic measure with respect to the surface measure. For the latter, one can study it qualitatively and quantitatively. Okay. And to state some results, let us first give several definitions. Our n-bin space is n plus 1. And it adds at least two. It adds at least two. Hn denotes the n-dimensional hostile measure. The set E is called n-dimensional alpha-divided regular. If the hostile measure of E intersects the ball, is compared to the radius power n for each point. From the definition, it tells us that E is n-dimensional. Also, if the hostile measure is restricted to E, it's a W measure. Next, E is called n-dimensional ratifiable if it's almost everywhere covered by. If it's almost everywhere covered by a counter union or Lipschitz graphs. Here, F each Fi is Lipschitz from n to n plus 1. Let us see another notion. E is called n-dimensional uniformly ratifiable if it's n-dimensional alpha-divided regular, and for each point x and for each radius, there is a Lipschitz mapping rho with the normal controlled by a m such that the following estimate holds. The hostile measure of E intersects the ball, intersects the Lipschitz graph. The measure is greater than theta r power n. this condition says that E has big pieces of ellipsis graphs. In fact, this quantity is comparable to R power n, because here E is n-dimensional ADR. Then the Hausdorff-Meyer E intersects the bar is compared to R power n. Yeah, there's a definition here. The uniform reliability was introduced by David and Simmons. It's a quantitative scale invariant version of reliability. In particular, the uniform reliability implies reliability. It can be seen from this picture. Here, I put a picture. Because for each ball centered at the boundary, one can get a portion of the boundary. Here, the left-hand side is the ellipsis graph. The portion is a ellipsis graph. The moving is about on the boundary. We can cover the whole boundary. We introduce more definition. This picture will help us to understand them. Consider an offset omega. We see that omega satisfies a Cockcroft condition if for each surface bar. Here is a surface bar delta, and B is a corresponding bar centered at the boundary. For each surface bar, the bar B contains another small bar B x delta CR in omega. Here, the constant C is a uniform, and the x delta is a Cockcroft point relative to delta. And from this definition, we see that the Cockcroft condition is a quantitative scale invariant version of openness, but it's stronger. It's stronger than the openness. The next one is the Harnack chain condition. It means that for every x, x1, x2, there is a finite sequence of balls in omega connecting x1 and x2, such that bk meets bk plus 1, and the radius of bk is comparable. The radius of the bk is comparable to the distance from bk to the boundary, where the number of the ball depends on this ratio. Here, delta x is the distance from x to the boundary, and here this is the picture. Here is x1, x2, and we can find a sequence of ball connecting them, and bk means bk plus 1. And from the definition, we can show that the radius of each ball is compared to the distance from the boundary, from bk to the boundary. And we notice that the Harnack chain condition is a scale invariant version of path connectedness. To understand this definition, we present two examples. Let us see the point Z here. It's here it's very narrow. Sorry, my picture is not so good. Here it's very narrow. We cannot find a small ball with radius compared to the large balls. So the Cockcroft condition fails at this point. Let us see the points Z1 and Z2. They are very close to the boundary, but the distance from Z1 to Z2 is compared to delta Z1, delta Z2. So this ratio is comparable to 1, but it needs a lot of ball to connect these 2 points. The ball should be in the domain. Thus, for these 2 points, the Hannigan condition fails. We here give another example. Here it's a ball, but we remove one radius. We choose x and y are very close to the boundary, such that delta xy equals delta y. Delta x equals delta y equals the half of the distance from x to y. Then this ratio here, this ratio equals 1/2. As before, we need a lot of ball to connect these 2 points. So the Hannigan condition fails, but it satisfies the cultural condition. It's used to check this. This is a cultural and Hannigan condition. Okay, using this definition, we define NTA and CD domain. Here, it means the non-tangential accessible domain. C means correct domains. Given open set omega, we see that it's one-sided NTA domain if it satisfies cultural and Hannigan condition. Omega is called an NTA domain if it's a one-sided NTA domain, and the exterior of omega satisfies the cultural condition. Okay. Omega a one-sided NTA domain with area boundary is called a one-sided car domain. And any domain with area boundary is called a car domain. Yeah, this is a definition. We need we here give another notion. Omega is a uniform domain. If there are uniform constants C1, C2 such that for array x1, xy in omega set, there one can find a good path gamma. The good path means that the length of gamma is compared to the distance from x to y. Also, the second condition says that the path is not very close to the boundary relative to the distance z from the distance from z to x to y. Okay, and actually, the uniform domain is equivalent to one-sided NTA domain. It was proved by Azam, Hoffman, Mattel, Nystrom, and Tosa in 2017. Let us see the following relationship. Lib domain is stronger than BM1 domain. Here, the BM1 domain means that the boundary of the domain is given by a BM1 function. If for function u, if the gradient u in BM1, we see that u in BM1. And the BM1 domain is stronger than NT domain. NT domain is stronger than one-sided NT domain. As we told, one-sided NT domain is equivalent to a uniform domain. Okay. Next, let us introduce the elliptic measure. In what follows, we will consider we always consider second-order definitions from elliptic operators. The coefficients satisfies the uniform ellipticity condition. The matrix A is not necessarily symmetric. Okay, and what is the elliptic measure? Given elliptic operator L, one can construct a family of regular Borel measure omega L. Omega L is a family. Omega L X is called the pool. X in omega, such that for every boundary data F continuous on the boundary with compact support. If we define U as the integral of F on the boundary with respect to omega X, then U is a weak solution of the Dirac problem, and on the boundary U equals F in some sense. Here it only needs the openness omega to construct the elliptic measure. We mentioned that if the boundary is Wiener regular, then the solution is continuous up to the boundary. Also, if omega is bounded or the boundary is unbounded, then the elliptic measure is a probability. And if omega is bounded and the boundary is if omega is unbounded and the boundary is bounded, the elliptic measure is not a probability. For example, we can consider omega is a complement of a ball. Then omega is unbounded, but the boundary is B. It's bounded. Actually, if omega is bounded, the elliptic measure of E is a probability that a particle with a burning moment leaving from X escapes from omega through E. This is the meaning of the elliptic measure. Okay, we have given some definition. Let us talk some results related to uniform verifiability. The previous definition of UR is geometric. We are going to present several categorizations of uniform verifiability. The first one is analytic. It states that the UR is equivalent to the Kashmir estimates for the second order gradient of single layer potential. Here, SF is a single layer potential. E is the fundamental solution of Laplacian in n+1. In practice, it's an important criterion to show a UR. Okay. And next, we consider the singular integral operator. Here is a definition. K is an order function, or a smooth function such that the GS gradient is controlled by X power minus G. In 1993, David and Simmons proved that E is uniformly verifiable if and only for the singular integral operator is bounded on R2 space. This result tells us that the UR sets for which all sufficientness singular integral operators are bounded on R2. Here, the truncated operator is used so that we do not have to show the existence of principal value integral. Let us see a particular singular integral operator. At the same time, David and Simmons conjecture that the uniform verifiability is equivalent to L2 boundedness of Riesz transform. Its definition. The full conjecture was solved by Nazarov, Tosa, Uberg in 2014. Before that, in 1996, Martina, Mingming and Vandala showed that David Simmons problem holds for a Cauchy integral that is true in for dimension 2. In 2014, Hoffman, Martel, Mebarda proved the case. E is a boundary of a one-sided Carl domain. And recently, this result has been extended to the gradient of the singular potential by Blada, Bliadi, and Tosa. In this result was proved in 2019. Here we mentioned that in another paper using this result, Tosa proves that if every bounded harmonic function satisfy a Cauchy-Meyer statement or absolute approximability, then the boundary is uniformly ratifiable. And in their proof, they used the connection between Ries transforms and harmonic measure, but this connection is invalid for the general elliptic or elliptic measure. Okay. Next, we turn to the absolute continuity of harmonic measure. We will use sigma. We will use sigma to denote the surface measure. That is, sigma is the Hausdorff measure reached to the boundary. Okay. The first result was given by F and M Rees for a simply connected planet domain. If the boundary is uniform, if the boundary is ratifiable, then the harmonic measure and the surface measure are mutually absolutely continuous. In 1990, Bishop and Jones proved that if only a portion of the boundary is ratifiable, then harmonic measure is absolutely continuous with respect to the surface measure on that portion. They also construct a counter example to show that without connectivity, the first result fails. Okay. And recently, a remarkable result was given by Hoffman, Mattel, and others. It only requires omega is open and the surface measure of E is finite. The absolute continuity implies the ratifiability. It's a very general result. Here we don't talk the results in Lipschitz domain. We directly introduce some recent results in the more general situation. The first theorem is a summary of several papers. Here, omega is a harmonic measure. They prove that omega in infinity is equivalent to the boundary is UR. It's also equivalent to omega is a Carl domain. A infinity implies UR was proved by Hoffman, Mattel, Uliadi in 2014. UR implies a Carl domain were proved by Azam, Hoffman, Mattel, Nistrom, and Toro in 2017. And Carl domain implies infinity is a very early result. It was shown by Simmons in 1989 and independently by David and Jensen in 1990. This result connects the absolute continuity of harmonic measure, the regularity of the boundary, and the geometry of the domain. Okay. The second theorem is significant. It doesn't need the Hanegin condition compared to the first result. It removes the connectivity, and A infinity is replaced by weak infinity. To get the equivalence, it requires a weak local joint condition. Here, Oh, sorry, here I didn't give the definition. We just want to see what happens without connectivity. Also, atoms 2 and 3 give a geometric characterization of appreciability of the Dirac problem. And from atoms 1 and 2, and we see that A infinity actually is stronger than UR in the general situation. Okay. And let us see what happened to the general elliptic measure in one-sided card domain. Omega L infinity with respect to the surface measure. If I know if every bounded weak solution of L satisfies the Casimir estimate, here is the it's called the Casimir estimate. This result was obtained by Gabriel Hoffman, Mateo, and Toro in the connected situation. It can be used to show the perturbation of infinite property. And if the energy condition is removed, some kinetic Mogul-Tau proves the following result. The boundary is uniformly stratifiable if and only if every bounded weak solution U of L and L transpose satisfy Casimir estimate. Yeah, L transpose is transpose operator of L. Compared with the previous result, this theorem requires the coefficients satisfies the R1 Carson condition. And the infinity is represented by U1. As we told before, A infinity is stronger than U1 in a general situation. Okay, next, let us see the relationship between infinity and UR for the general elliptic operator. Omega is a one-sided Claude domain. Assume that the coefficients satisfy the following: A is Lipschitz locally. The gradient A times delta in R infinity, and more importantly, the gradient of coefficients satisfy a Casimir estimate. Here, this is a Casimir estimate for the coefficients. The conclusion is corresponding to the harmonic measure case, and they also prove that the Carson condition is sharp to guarantee infinite property. Actually, this result is a double case conjecture, and Keeling and Favor made the first attempt to made the first step on the bounded elliptic domain and give an affirmative answer. And in one-sided Claude domain, Hoffman, Mateo, and Toro proved the same result whenever the gradient of coefficient satisfy R1 Carson condition. Here, if we remove the, it means if we remove the power and the delta, it's called R1 Carson condition. And here the gradient A times delta in R infinity, then we can see that R2 Carson is weaker than R1 Carson. And the result here is sharp. Okay, we here mention some relevant work in elliptic domain. The absolute continuity of harmonic measure was studied by Dobberg, Phillips, George Klinge in 70s and 80s. For the perturbation theory, Feldman Klinge formulated the Carson perturbation on the coefficients. Their result is also sharp. Recently, it was extended to the one-sided color domain by Gavero, Hoffman, Mattel, and Toro. And it contains the large and small perturbation. After that, Fenoy, Miborda, and Pagi established the similar results on the lower dimensional sets. In another direction, UR is also equated, is also related to the approximation of harmonic functions. Hoffman, Miborda, and Tosa, and others obtained some excellent results. And finally, BM solubility of the Dirichlet problem was also studied. Hoffman and Lee studied the non-connected case. Miborda and established a result on lower dimensional sets. Next, we introduce our results. We need some notation. We see that an open set omega satisfies the capacity density condition if the capacity of the closure of the ball minus omega relative to the double ball. The capacity is greater than r power n minus 1. At the beginning, we defined the ADR condition, and one can show that ADR implies CDC, and we are gonna work in the one-sided ND domain and satisfying CDC condition. Okay. We also define the canonical square function and the non-tangent maximum function in the following way. Here, gamma alpha x is a cone with the vertex at x and the aperture alpha. Similarly, we define the truncated square function and the truncated non-tangent maximum function. If the cone is represented by the truncated cone. Okay. Okay. Given the second order division from elliptic operator L, we always consider this kind of solution. And we see that L is LP soluble with respect to omega, with respect to elliptic measure omega L zero. If for array alpha and n there exists a uniform constant such that the truncated non-tangent max function is controlled by f in LP for array surface ball. And L satisfies a Casimir estimate with respect to omega L zero if this inequality holds. Compared to the previous Casimir estimates, the surface measure is replaced by the elliptic measure, and the distance function delta is replaced by the green function. Here, GR0 is the green function related to L0. L satisfies S less than estimate in RQ. It means the truncated square function is controlled by the non-tangent maximum function in RQ. And the next one is BM solubility. L is called L is BM soluble with respect to omega L0 if we define U L omega is a measure of the boundary, then following Casimir statement holds. Compared with the previous Casimir estimate, we put this term f delta F0 is the average of f over the delta with respect to omega F0, and this expression is similar to Casimir above, but as we did before, the elliptic measure may be not a probability. If the elliptic measure is a probability, then UR omega is a constant. So we can remove this term. Finally, we see that L is Bion solvable in the sense of Hoffman B, and if the following estimate hold. Compared to the Bion solvability, it removes this term, but on the right-hand side, it needs a new estimator. Here, rho absolute equal to 0, as absolute tends to 0. Yeah, this is our definition. Using this notation, we now state our theorem. We consider second-order divergence from elliptic L and L0. Our background is one-sided NTA domain and satisfy a CDC condition. Omega L in infinity, which is omega 0. Here, A infinity is defined as a union of reversible class. B, L is observable for some P bigger than 1. C, L satisfies Cartman estimate with respect to omega 0. L satisfies S less than estimate in LQ for some Q positive. L is Bion solvable. Last one, L is Bion solvable in the sense of Hoffman-Lee. Then we can prove that all the properties above are equivalent. And our background hypothesis, we don't know any information about the surface measure. As we told before, ADR implies CDC. In our situation, the surface measure may be bad. Using our theorem 1, we immediately obtain a corollary. If L0 equals L, the Ladon-Nikodym derivative of omega L with respect to omega 0 equals 1, then omega L infinity with respect to omega L. That means item A holds. Then using our theorem, we can get the corollary. All the properties B to F hold for omega L. Our theorem can be used to study the perturbation of elliptic operators. Consider L and L0. We define rho as a disagreement between A and A0. Then we define the Cartman estimator. We have seen this kind of condition for the solution U. That is, if rho order is replaced by U, then it becomes the Cartman measure estimate for U. And this kind of perturbation comes from the work of Feldman, Killinger, and Pfeffer. They studied the perturbation of elliptic measure in infinity, which is the surface measure in elliptic domains. They also proved that the Cartman type perturbation is sharp to guarantee infinity property. Let us see the following quadratic estimator. The integral is taken over the cone, and this form was used by Feldman. It's related to the cone. It's related to the canonical square function. If we replace if rho order is replaced by U, then it becomes the square function. Okay. And our theorem is our domain is the same as before. It's a one-sided NTA domain satisfying capacity density condition. The first conclusion says that the Cartman estimator, if the Cartman estimator is finite or the quadratic function is L infinity, then all the properties A to F are satisfied. In fact, and this assumption, ICMAT, Hoffman, Martel, and Toro prove that omega L in infinity with respect to omega 0, then then using this result and our using that result and our theorem, we can get all the properties. Let us see the second conclusion. Given P is bigger than 1, one can find a small absolute P such that if the Carson norm is small, or the L infinity norm of a quadratic function is small, then omega L in reverse hold P prime with respect to omega L 0. This result was proved by ICMAT, Hoffman, Mattel, and Toro. Then using this result and our theorem, we got that L is RQ solvable for every Q is greater than P. Okay. The first result is called the large perturbation, which it wants to maintain A infinity property. The second one is called the small perturbation, which it wants to get a better result. That is omega L in reverse hold class. And next, we will obtain a qualitative analog of the previous equivalence. The background hypothesis is same as before. Then we get that there exists some alpha 0 depending on the geometric, such that for every alpha is greater than alpha 0, and for every elliptic operator, the following are equivalent. Omega L0 is absolutely continuous with respect to omega L. It's equivalent to that. We can decompose the boundary into the union of Fn. The measure of F0 equals 0. Fn can be written as the intersection of the boundary of omega and omega n. Here, omega n is a subdomain with the same property as omega. And for every bounded weak solution, U of L, the truncated square function in LQ or locally with respect to omega L0. This is also equivalent to the truncated square function is finite almost everywhere for almost everywhere with respect to omega L0 for every bounded weak solution U of L, and for every R. P. The last one is also the finiteness of the truncated square function. But here R depends on the X. Depends on X. Okay, this is the characterization of omega 0 with respect to omega 0 is absolutely continuous with respect to omega L. Let us see this. Okay, this result says that the absolute continuous can be characterized by the local RQ estimate for the truncated square function. It's also can be characterized by the finiteness almost everywhere of the truncated square function for the bounded weak solution. Okay, let us compare this result with theorem 1. Here, we prove that omega L in infinity is equivalent to Carson Mayer estimate, and it also equivalent to S less than S estimate. Theorem 4 is a qualitative version of theorem 1. A infinity turns into absolute continuity. The qualitative analog of S less than estimate becomes into the local RQ a local LQ estimator for the truncated square function, and the Carson-Meyer estimator is also connected to the local LQ estimator for the truncated square function. Okay. Next we are gonna use the equivalence between A and C to choose a perturbation. Let us see our results. There exists the alpha zero such that if the quadratic estimator is finite amongst the quadratic, this is a truncated quadratic estimator is finite amongst the area with respect to omega L zero. For some R, for some alpha, for some R, then omega L zero is absolutely continuous with respect to omega L. And let us compare this result with omega L in infinity. Here we told that to get the omega L in infinity with respect to omega L zero, it requires the quadratic function is bounded. But now to get the absolute continuity, we only need the truncated quadratic function is finite almost everywhere. The theorem 5 concerns the perturbation between L and L0. Next, we consider only one elliptic operator and study the perturbation between L and L, the transpose of L and the symmetric part of L. Assume that the anti-symmetric part is ellipses locally, and define this quantity. Here the divergence denotes that the divergence operator acting on the columns. If f R is finite almost everywhere with respect to omega L, then omega L is absolutely continuous with respect to omega L transpose, and with respect to omega L sim. L sim denotes the symmetric part of L. The second conclusion is that if f alpha R is finite almost everywhere with respect to omega L and with respect to omega L transpose, then omega L and omega L transpose are mutually absolutely continuous, and omega L is absolutely continuous with respect to omega L sim. Okay, as we told before, and the perturbation result is an application of the equivalence between A and C. That is to get the absolute continuous. To get the absolute continuity, it is sufficient to show the truncated square function is finite almost everywhere. Okay, and here we have so far we have formulated all of our results. We mentioned some estimates in our proof. The first, the geometry of a domain is crucial to us. The existence and the properties of the dielectric grid on the boundary are established by ICMAT, Marginal, and Theorem. Based on the dielectric grid, one can define the sawtooth regions, their subdomain of omega, and have good geometric properties. Also, in each sawtooth domain, the green function is comparable to the distance function delta. Moreover, one can construct cutoff functions adapted to the sawtooth domains. Those cutoff functions are very useful to establish some PD estimates. On the other hand, many proofs are reduced to the dyadic scenario. So it needs some techniques of dyadic analysis. We also need some PD estimates. Borges estimates ensure that the elliptic measure is non-degenerate. CFM's estimate established the relationship between elliptic measure and the Green function. It connects the geometry and the PD. We also need the lower bound of dyadic square function. What behind this estimate? What behind this estimate is geometry information. If the measure of f is small, one can find a good curve of f. Based on this, one can construct a solution in this way, such that the dyadic square function has a lower bound. It provides us great convenience because this estimate connects infinity as less than estimate and the Cauchy measure estimate. The strategy of the proof is as follows, but we don't talk the details. Okay, that's all. Muchas gracias.
We thank Mingming again for the very nice talk. Thank you very much.
Thank you, Jose.